Okay, so welcome back. It's JM from Python's tutorials, and we continue with chemical equilibrium. In the tutorial sheet we were solving yesterday. So that's why we have started from question 5. So question 5 directly, it says the equilibrium constant is 0.0900 at 25 degrees Celsius for this reaction here. Now, for which of the following sets of conditions is a system at equilibrium? So for those which are not at equilibrium, in which direction will the system shift? So what we have here is this. So these have all been given in terms of partial pressures. So we have things like partial pressure of water. That's the normal way that should have been written. ATM, like that. Okay, so how are we going to find the equilibrium constant for these partial pressures? So first of all, we write the formula. So the formula from this is Kp is given by partial pressure squared of HOCl over PH2O and partial pressure of Cl2O, something like that. So this is the formula that we use. So we'll just be using that same formula throughout. So here we just say Kp is equal to partial pressure squared of HOCl over partial Cl2O, which is going to be, so here of 1 atm, this one. So squared over partial pressure of water is this. So we have 1 here times partial pressure of this one, also 1. So this is just what? 1. Now the question is, are these two equal? So we know that Kp, so K is, so that means Kp is not equal to what? K. So we're saying K is not equal to Kp. Why? Because 0.09 is not equal to 1. So we're giving 0.09 there. So it's not giving us 1. So then that means that we're going to say, therefore, the system is not at equilibrium. Now they ask a question to say, if it's not at equilibrium, we should state in which direction the system will shift. So the system in this case is going to shift how? So here K is 0.09. This one is less than 1. So I have K less than, so K less than, so K is less than Kp. So since K is less than Kp, we're going to say the system will shift what? To the right. So you just follow where this arrow is pointing to. So it's pointing to the right side. That's where the Kp is. So the system should shift to the right side. So B, we have this one. Again, here we'll say Kp is equal to P squared HOCl over P squared H2O and P, P then Cl2O. So let me just make a correction for water. Water, there's only one more there. So this is going to be what? 21.00 squared over, this is 200 times 498. And that is going to be what? So 21.100, this will be 4441, and then divide by, yeah, so 2100 is 441, 21 squared, oh, it's 441, sorry, okay. So we just have this 441 over 200, so 200 times 498, so 498, so 200 times, it's a 49.8, not 498. So it's 9960. So there's a point here. So now I have 441 divided by answer. So this gives us 0.99 0.044. Now we compare 0.044. That means 0.09, which means not. Now, since the system is not at equilibrium, how is it going to shift? So here we know that because this is our Kp and the other one was K. So here we're going to say K is greater than what? Kp, because 0.09 is greater than 0.04. So that means that here this to the right, because it's pointing on the right hand side. So I would like you to do the next one. So why we were just using the toe here is that it's because each one of these they are all in toes. There's nothing like this one is in ATM, that is atmospheres. So you just have to use the same unit for every case. If that's what they have given, then you go on with the same. So now you do number C. That's an exercise. So you can pause the video from here and see how you're going to move. So I give you 10 seconds to do that. Okay, so I hope you did that, you finished it. So just confirm your answer with me. Again, we say Kp is equal to the square over the R2O. This is going to be 2296 times 8 over, this is what now? 296 times 15 is 4440. So 400 divided by that number is 900 and then 9. So numbers move like that. So this is just near what? It's just equal to 0.09. Remember that in the main system we've been given 0.09. So you are just supposed to make sure you find that it's the same and that you state that the system is at equilibrium. So just in case you haven't yet subscribed to our channel, and of course we haven't been around, like you have never checked our tutorial, our videos before, so and this is your first time, I would like you to like our videos as well as subscribe, because when you like, you give us more confidence to put better content on our, to improve and make sure we provide quality education. And when you subscribe, that means you always receive notifications whenever we upload new content that we wouldn't like you to miss. Yeah. Gets you to be of need. You can also share with others, let them know about par excellence tutorials, especially on YouTube. All right, thank you. Let's do now question 6. It says, at a given temperature, 0.0300 or more of nitrogen dioxide and all those others were pressed in a 25.00 liter container. The following equilibrium was established. Now they are saying at equilibrium 0.06 mole was present. So calculate the equilibrium composition of the gases. So here, we'll be likely, we'll need to use the IC tables. So we have the reaction 2Cl NO 2 CO2. So the first thing we're going to do is we're going to put initial number of moles inch. After change, we're going to go to equilibrium concentrations, equilibrium number of moles. So the initial number of moles here was for this 0.03 is for nitrogen dioxide. .300, and then we have 0.200 and 0.500. Now The change here is going to be negative x. So there's a 2 there, it's going to be 2x. And the change for the product is always positive, so positive x, and this is positive x as well. One will be, we'll have a 2, which is 2x. Now, the equilibrium concentration of this is given as 0.600 mole. So now we're going to say 0.5 give us 0.600, which is equal to 2x. 0.5 minus 0.6 negative 0.1 is equal. So x is equal to negative 0.05. So that is the change. So it's negative 0.05. So x is a negative value. So then what will be the equilibrium concentration of nitrogen and the others? So we put negative 0.05 there. So from 3, we're going to say 3 plus negative 2.05, and 2 minus that. So let me just try to use a calculator. 3 minus 0.05, so it's 2.95, and then 2.00 minus 0.05, it's 1.95. These are equilibrium number of moles. So to get the concentrations, we're going to divide by the number, the number of liters, or rather the volume of the whole solution, because molarity is given by number of moles of solid divided by the liters of solution. So here what we have is this. These are equilibrium concentrations, equilibrium number of moles, I mean. So to get the concentrations, we're going to say the concentration is equal to 0 liters. So 0.600 mole over liters, which is 0.6 divided by 25. So this is 0. And then the concentration of the N2O95 mole over 25. So 2.95 divided by 25. So this is 0.118. And the last one is 1. This is 0.078. So those are the equilibrium composition of this gas. I hope that one was clear. We go to question B, which is determine the Kc for the reverse reaction. So here, first of all, we need to know the Kc for the forward reaction. So Kc is given by what? Kc for the forward reaction will be given by, so we look at the products, which is N2O and CO2. And then we divide this by CIO. Like that. And this is going to be equal to, so for nitrogen, the concentration is squared, and CO2 is 0.078. Then the last one is that, which is 4M. So this is squared. So we have 0.118 times 0.0 divided by divided by 0.024. So this gives us 9. So for the reversible reaction, 1 over that number. 979 1 divided by us 0.06. And we calculate the Kc for the above reaction. So the Kc is one that we were just found. So Kc is equal to, we start with the reactants, which is going to be squared over 0.6, and then we multiply this by what? So that's the one. So this is 0.9. So we have 1 divided by us. Okay, so this one, let's just remove. There's a simpler way we can go. Like that to just K C. KC in this case is just equal to KC is equal to KCF, which is for the forward. So it's just going to be 15.979. We're going by this because that's how the reaction is. The reaction is this one here. So this is a reaction. So that's the formula we're using, which is forward. So it's the same as for the forward. But for the reverse, it will be 1 over that, which we have already gotten. Okay, so we go to question 7. Question 7 says for the reaction, this one, Kp is given there. And then given that Kp, when the partial pressures of the gases are expressed in bars, what is the Kc for the reaction? So for us to get the Kc, I think because I didn't leave space for this one, for us to write this one, we're going to say we're going to first find the delta n. So delta n is equal to summation of stoichiometric coefficients, so which is x for the products minus summation y. So the summation of stoichiometric on the products minus 2 on the reactants, which is going to be -1, is equal to Kc open bracket delta n. And that means that So our Kp is 7.3 is equal to Kc, then Rt, that's what, so the Rt is 0. So let's just write it 1. So remember, we're looking for Kc. So we divide by Rt to the power negative 1, even here Rt to the power negative 1. So this cancels 7.3 over Rt to the power negative 1, which means that we are multiplying here by what? Rt. So that would be what? So we say 7.3 times the value of R. So here we can just put the value of R. So since we haven't been given the value of temperature, times 0.08 3145, then T. So that is going to be 7.3 times 0.083145 is going to be, so this is going to be 0.607 T. So that will be our Kc for this reaction. Okay, so we go to question 8, which says predict the shift in the equilibrium position that will occur for each of the following reactions when the volume of the reaction container is increased. So if the volume of the reaction container is increased, what's going to happen here? So what we have to be looking at here are the stoichiometric coefficients. So here we have 1 plus 3, which is 4. And then here we have 2 stoichiometric coefficients, which means that we have more here as compared to on the products. So because of that, we're going to say we shift to the right. So we shift to the right, simply because there we just have 1. We just have 2, what's this? So this one we should write. So the way you do this, let's say we have B plus D. Let's say here we have 2, and here there's 1, and then here we have 5. So you just have to find the total number. So the total value of stoichiometric coefficient is 2 plus 1. The stoichiometric coefficient there will be 6. The shift should be on the side where there are few. That's what happens with energy, with volume, because the more you increase volume, then even the number of moles increases. So remember that volume and number of moles, there's that gas for gaseous state. Okay, so simple. This one is already clear there. We're going to shift to the what? We're going to shift to the left. So we shift to the left because here we have 1 plus 1, 2. There we have 1 left. Okay. So I hope it's now simple. I give you a second for that one. You can pause the video and answer it. Okay, so we have H2 plus this. Here, this would be 1 plus 3, which is 4, and this side shift to where 2 is, which is the what. So shifting should be on the right. But how about you had this H2 plus F2? So, and that's 2. So there's no shift. So it's equal number of reactants and products. So there should be no shift. So I hope that was a good example, because it's taking something that we have not looked at in a while. Okay, so for the following reaction, write how each of the following changes will affect the indicated quantity, assuming a container of fixed size. Write increase, decrease or no change for the chemical added. So write how it would respond after addition. So H2, when we add here, what will happen to the value of oh, there's also H2. What's going to happen to the value of Br? So it has no effect. No effect. So that will be no change. Even here, no change. And there. So now what will be the change on the K value? What will be the change on the core on the K value? If we increase some more H2, so since we have added some more H2, which means that H2 has increased. So here there's an increase. But how about the reaction? H2 is here. So the let's write is equal to the power 2 over Br2. So H2 and Br2 are in the denominator. So if more H2 has been increased, then this value reduces. And then HBr is added. So on Br2, there will be no change. And then HBr, meaning that it has been added. So increase. Then K value, then this will no change. Okay, H2 has been removed. So if H2 has been removed, Br has no change. SBr, no change. K value, the K value, if that one has been removed, so it's going to increase. And then H2, what will happen to H2? Since H2 has been removed, so it's going to reduce. Okay, HBr removed. So where we have where Br, so there will be no change here. And then this one HBr reduced. It has been moved. Then K value will reduce, and then H2 value will be what? So there will be no change here. No change. So when the temperature has been increased, what will happen to the whole of this reaction? When the temperature has been increased, so this also depends whether the reaction is exothermic or endothermic. Yeah. So we can take maybe this reaction as exothermic. So that means that when temperature has been increased, then the exothermic reaction is favored. So the exothermic reaction is the one where energy is given out. So if energy is increasing, what the temperature has been increased, what will happen? So if the temperature has been increased, so what we are trying to produce, the value will change. So this will also increase, and the H2 also reduce, and the K value is going to increase. And then if temperature is decreased, so this will increase, this will reduce. So that's how it goes. The pressure is contained in the container volume measured. Oh, we have to do question 10. Okay. Question 10 says, in the following reaction, what conditions would favor maximum production of ammonia? So for us to produce more ammonia, so ammonia is the product there. So what conditions would favor maximum production of ammonia? So what would favor maximum production of ammonia is addition of a temperature. So energy, heat energy should be more heat energy should be added. And what else can we do to produce maximum of ammonia? So the ingredients also should be readily available. They should be in full. So we can also say, and then also add into. So those things can help us. So the other way is to remove 3 as well. While they're producing it, you remove it, and then some new ones will be there. So that way the reaction can take in a faster way. Question 11, consider the solution of, so this is a saturated solution of copper 2. When dissociate this, we get aqueous OH, like that. Now they said, write the KSP expression in terms of the concentration of copper 2 ions and hydroxide ions. So this is going to be copper 2. So we're going to say KSP. In aqueous, this one is solid. So this is S. So this is going to be times the concentration of HO to the power 2. So that would be our KSP. Okay. Then now we have this one, calculate the solubility S and pH of the saturated solution of that. So just from what we have done previously on top here, we're going to write this SP times H O negative squared. So now what we are going to do is we break this. So where there's KSP, we write it as what? In terms of solubility S. So this is going to, we'll have the solubility times it. So if we check the reaction, there's a 2 there. So we're writing this as 2S, which is 4S cubed. Now that this is 4S cubed, then what's the value of S? So we're going to say KSP is equal to that. So we're going to say KSP is equal to 4S cubed as well. 1.6 by, we divide through by 4. Yeah. So we're going to have 0 times 10 power negative 20. Let me just confirm that. 1.6 exponent negative 19 divided by 4. Okay, so it's correct. So now, having found that, we're going to find the value of this. So it's 10 power negative. So the cube root and 3 is going to cancel, the S is equal to, so we get the cube root of this, which is to the power 1 divided by 3. Okay, so this is 3.419995. So we just prove. Now that this is the case, we're going to find the pH. So pH. So the log of the wax is for hydrogen ions. Now in this case, we don't have hydrogen ions, but the positive ions we have are those for. Okay, so pH, that's the pH. It's negative log of that, of which we're going to say pH of, instead of that, now we're going to put HCU 2 positive, because negative log 2 times 10 power negative 7. So the log So now the log of this. So which means we have 6.4. So this is the pH value, 6.466. I hope you're able to follow through. Yeah, the last ones just became a little tiresome, but I hope you managed to understand. Okay, so consider AL3 KSP with that. Determine the mass of that will dissolve in that. So here we'll go back to the same. We're going to say that 3 is equal to what? 6 plus OH negative. So that's what we're going to have. And in this case, we're going to say, since that's what we have, and we have been given the what is, so we write this in form of S. So this will be S solvate is equal to so the solvate will be multiplication of the solvate of this, which is this is L3. So S times 3 of that. So we say 3S to the power 3 power 4. This is now the case B. Now the case B here was given as 3.10. So the KSP was given as 3.0 times, so divided by 27 and by 27. So this is going to be 3.0 exponent negative 34. So that means that S to the power 4 times 10 power negative 34. Oh. So we divide this by 27, which is okay. So times 10. Okay, so now, but they are saying how much will dissolve in water. So what we have found is what we are trying to find here is more like the number of moles.